It's placed around some critical infrastructure, typically embassies, and these then prevent car bombs and truck bombs, but that doesn't prevent smaller bombs. We call them backpack or briefcase bombs. People can walk in between, but those are small bombs and their effect is limited as well. So here are some examples of bulwarks. They have to be strong enough to be able to keep impact forces away, and you can use barriers, passive and active. But the cost of retrofit or cost of hardening comes down very drastically if you increase standoff distance. So here, horizontal axis is you move to the right, shows standoff distance. Vertical axis is cost, and it comes down. So you can mitigate blast threat by increasing standoff distance. Another factor I said is the shape of the building. I already talked about reflection. Reflecting of blast wave from the face of a wall is one thing, and capturing blast wave inside the building or buildings that have re-entrant corners. If the blast wave is captured in a closed environment, it hits one wall, it reflects, it amplifies. It comes back and hits the other wall, it amplifies again. So for interior blast effect, for example, underground parking is a big challenge. We were involved in assessing a Jewish school in Montreal, and they said that they wanted to build a school on top of a public garage. And they said, what if there's an explosion in the underground parking? You have to protect our structures. I said, this is very big challenge. They said, no, we want you to show you if it's a challenge. So my student did dynamic analysis. He came up with 2-inch thick steel plates to put around columns to protect them. Even then, it didn't work. Why? Because this reflection of blast shock waves amplified the problem. So confined environment as opposed to unconfined air attack are two different things. So I already mentioned the importance of having high mass to increase inertia resistance, and again, reinforced concrete seems to be the best material. As a structural engineer, I feel uncomfortable about talking explosives, but I guess we all do interdisciplinary research, so I have educated myself about explosives a little bit, so I'd like to share that with you, because you want to know where these forces are coming. Just like in earthquakes, we're not seismologists, but we have to know the effect of seismology. So, explosives can be divided into three: chemical explosives, nuclear explosives, and physical explosives. Physical explosives are something that is placed in encased environment so that when it detonates, the fragments of that encasement flies out. It's usually under slower speed, and it doesn't last that long. Chemical explosions occurs when chemical material of explosive is oxidized, which means it's burned inside, and it creates tremendous energy, which then translates into shock waves, and these shock waves move towards the building. And I'll show you examples of building loading. But this happens in a very high supersonic velocity. Okay, so chemical explosions are measured in milliseconds. We have 5 milliseconds to 50 milliseconds, depending on the standoff distance. And then nuclear explosion is altogether different category. We all know that when you play with atomic makeup of nuclear materials, then in this case, very high but relatively slow wind loading keeps coming on the structure. They can be measured in the order of minutes, not milliseconds. It keeps coming, it keeps coming. That's why there's a widespread destruction. So we will here focus our attention to chemical explosions. And I already mentioned that when we talk about explosives, we talk about the charge weight in terms of TNT equivalents. Here you see different explosives and TNT is right here, and conversion factor is 1, and then if you have RDX, you have to increase it by 1.1. AMPHO, which is artificial fertilizer, which is quite commonly used, you have to multiply by 0.87. So these are conversion factors, but they're all around 1, so using TNT as a reference point for chemical explosives is a good one. In terms of typical civilian bombs, they range from pipe bomb, which is putting TNT into a steel pipe, to suitcase or backpack bomb, and they are usually 20 kilograms, so whatever someone can carry comfortably in a backpack, and they usually leave it right next to the structural member, so there's close-in explosion or contact charge. It's small explosives, but it may have a significant effect. And then you have different sizes of vehicular bombs, smaller cars and larger cars, vans, and trucks. Their effect, obviously, once again, is, depends on the standoff distance. If we were to take this yellow category van, so this is 500 kilogram bomb, 1,000 pounds, and then if you provide it at 10 meters, dotted line shows you that structural damage can occur, like columns can fail. So 500 kilograms at 10 meters is enough to bring building columns down. Or if you keep increasing the standoff distance, here this grayish green shows you 120 feet, right? It's now going to about 40 meters. Then you get walls, masonry walls, and fragments of that flying in and killing people. And then these dotted lines are glass fragments. So as standoff distance increases, which means you're moving up on this horizontal vertical axis, then of course damage decreases. That's another slide showing the importance of standoff distance. Here there's a comparison of car bomb versus truck bomb. Once again, there's a complex. The white area here is a facility that we want to protect. There are buildings nearby, and a car bomb explodes here, and then red circle is the diameter within which we expect structural damage, and yellow is non-structural damage. But if we increase that to truck bomb, then you can see the effect of explosion can be quite extensive and far-reaching to other parts of that perimeter area as expected. So, having covered basics, now we will look at loads on the structure. There are 3 or 4 types of explosions as it's related to location. First of all, if it's free air burst, let's say it's dropped by an airplane or something exploding up in the air, it causes spherical shock waves. And these spherical shock waves goes and hits the building. This is one category, and the movement and the expansion of the shock wave is in spherical nature. But if you have air burst explosion, which is slightly above the ground, and it causes this time semi-spherical, and then the magnitude of that is different. Now, if you put it right on the ground, as it usually is the case when we talk about car bombs and truck bombs, then the explosion, the shock wave reflects from the ground and it increases. So this is now called incident pressure in the air. It travels in a semicircular manner. It hits the building, it reflects, it increases 2 to 12 times the incident pressure. So these are dependent on where the explosion takes place. God forbid if you have explosions inside a building, as I have already mentioned, then you have confined or semi-confined regions where reflection of these shock waves take place between the walls, and then effect amplifies quite drastically. Now, how do we quantify them is the next question we will deal with. When an explosion occurs, then there's tremendous increase in temperature and pressure. We're talking about 10,000 kilopascals. In our lab, when we go to 100 kilopascal, that is our limit for window testing. Most US government, Canadian governments want protection against 100 kilopascals because that's the limit where glazed window can sustain blast. Now we're talking about 10,000 versus 100 kilopascal, just to put things in perspective. This is the amount of energy released and the pressure generated as soon as bomb explosion occurs. And then the temperature can go from 3,000 to 4,000 centigrades. And this violet explosion starts causing a shock wave. This shock wave is referred to as overpressure. Anything that is higher than atmospheric pressure in blast engineering is referred to as overpressure. But those overpressures that reflect from the ground is called incident pressure. So we will make reference to this terminology. And once again, when incident pressure hits the target and it amplifies, it reflects, it's called reflected pressure. And depending on the intensity of incident pressure, it can be 2 to 13 times the value of incident pressure. So reflected pressure becomes tremendous. Here I have animation obtained from CFD analysis, computational fluid dynamics analysis. We used Elastina, and you can model air pressure, and then it shows you the propagation of air waves. So after 8 milliseconds, the shock front reaches the building, which is referred to as arrival time. And then here we have 10 milliseconds, it starts increasing, and then 14 milliseconds, almost 2/3 of the front wall is covered. And then 18 millimeters, the entire last front face is covered, and this is the full reflected pressure. Then what happens is that the pressure clears away, it starts escaping from the sides and from the roof. This is called clearing time. And then it starts going towards the other side of the building, as you can see. Now there's no reflection pressure here, but there's incident pressure on side walls and the roof, and it keeps sweeping the building depending on the shock wavelength. And then it may start affecting from the rear wall, but with some time delay, and this is now 60 milliseconds after explosion. So this clearly shows you that shock front travels, hits the front, it tremendously increases, and then it clears, it escapes the front wall, and then it moves towards the sides and the roof, and then it engulfs the entire building, surrounds it with incident pressure this time. This is the pressure-time relationship. Of course, in structural engineering, we work with bed loads, line loads, wind loads, seismic loads. When it comes to blast, this is our load. We need to specify pressure versus time. It's a dynamic load, so if you hit an object, there's a time over which it changes, so it's a function of time. And when we do dynamic analysis, we have to use this pressure-time relationship. Here, the solid line indicates incident pressure, and then this is reflected pressure. This is the dashed line. And then there's positive phase, which is what we usually deal with. And then after the pressure is gone, then there's negative pressure behind the shock wave. There's vacuum, and then it starts pulling the building back. But then this is so small, this is called negative phase. In design problems, we usually ignore that. Now, after the front shock wave comes, then there's second wave in the form of so-called blast wind or dynamic waves arriving to the building. So what happens is that front wall is just like a shock wave is just like big wall of pressure, it moves, hits the building. As it's coming